Okay, so let's start with this. Because you need to understand the bigger picture. It says identify the hybridization of the carbon atom in the urea molecule. So, what do you have as an answer?
SP2.
SP2.
It's sp2 hybridization. Now, there's a couple of reasons how you can know this. One, around the carbon atom, how many regions of high electron density are there? 3. Okay? But that doesn't mean it's sp3. Because the S counts for 1, and then you've got 2 of the P's. So it should be sp2 hybridization. Here's the other thing, here's the other clue. Notice that you have a double bond with the oxygen. When you have a double bond, what type of bonds exist? Sigma and pi. What do you have to have a pi bond? A non-hybridized p orbital. So you could not have sp3 hybridization and that double bond with the oxygen. Okay? It's incompatible, I suppose.
So does my strategy of counting the number of areas of bonds it has and then subtracting 1 and then putting sp that number, does that always work?
Here's my concern, is that you could also have regions of high electron density where you have unbound pairs of electrons. So if you look at water, okay, that's sp3 hybridization on the oxygen. Because this has a couple of pair of unbound pairs of electrons up there. So the oxygen there is sp3 hybridization. Your best bet is to count the number of regions of high electron density, which would be 1, 2, 3. That's sp2. Okay. All right. Now, on solubility, here's the deal with solubility. Here's the general rule. Likes dissolve likes. So polars dissolve in polars, nonpolars dissolve in nonpolars. So when you're drawing a hydrogen bond, here's what's important. Is hydrogen bonding an intramolecular bond or an intermolecular bond?
Inter.
Just like the interstate. Okay, it connects states, right? Connects things. So here's the most common mistake that's made. First off, what 3 atoms does a hydrogen have to be bound to?
Oxygen.
Nitrogen, the oxygen, and the fluorine. But this, for example, I tried to redraw what was there in the middle. So this is a hydrogen, and then you have this nitrogen here. Is this a hydrogen bond right there?
No.
You're thinking
No.
intra.
That's intra, okay? This is not a hydrogen bond, okay? Could this oxygen here form a hydrogen bond with that hydrogen?
Yes.
Absolutely. That's an option, okay? So you could draw a dashed line between that hydrogen and that oxygen and that hydrogen on the end. That's an option. Here's the hydrogen, okay? And then you've got this nitrogen in here. You could draw a dashed line there. It just has to be between a nitrogen, oxygen, fluorine, and a hydrogen. But it's an intermolecular bond, okay? Not an intramolecular bond. Okay. So, B or C is just pretty much stoichiometry. You should get a molarity of around 18. Okay? Hopefully nobody looked at that and go, oh, I don't know how to find molarity.
Wait, we always do 2 decimals? Or 3 or 4?
Well, so here's the deal with this one. All the numbers that you were given here have at least 3 significant digits.
Let's just call it 3 decimals.
No.
That's not 3 sig fig. Just go 3 sig figs. You know what sig figs are?
Dude, that was first week, bro.
17.347 has 5 significant digits.
Yeah.
Okay?
No, it's 17.9.
You need to write that answer as like 17.9 molar. Now, if you put 18, they're not going to.
What about 17.95?
That's okay. Generally,
Too much though.
they give you one on either side. But here's what I'm telling you. You generally can't go wrong with 3 significant digits.
Okay.
Jonathan?
This may be a stupid question, but so it's exactly 17.948. So if you round that, would that round up to 18?
No, you look at the 9 to the right beside it. You have that 4.
Yeah.
So it just stays at 17.9. If you wrote it as 18.0, they're probably not going to throw a fit. But now, if you write 17.93432, they're going to throw a fit.
But that 4 doesn't round up.
Yeah. Big Mike?
So if I have .025, that first zero, that first zero after the decimal wouldn't count as a
Yeah, if you have .025, that has 2 significant digits. Okay. Now, on D, so let's talk about D. So, when it talks about the Chatelier's principle, the Chatelier's principle. So, the Chatelier's principle basically says, if you stress the system, it responds. Okay, that's all it says. Okay, like if I get stressed, I respond. Anybody does. So here's the deal. So if you look at your answer to C, that's 17.9 molar at 20 degrees. Okay? So then they're going to heat this thing up to 25 degrees. So when you heat it up to 25 degrees, what's happened to like the kinetic energy in the system? It's gone up. Now, you'll notice that it's saturated again, but now the molarity is 19.8. So at higher temperatures, can it hold more or less than what it was when it was colder? More. Okay? So you can think of it as, oh, there's more kinetic energy in the system. So if you look at that equation, and this is what it is, solid turning into a liquid, right? So to determine if it's endothermic or exothermic, look at what's happened to this. You have stressed the system. You have added heat to it. Okay, you warmed it up. You heated it up. You put energy in on the reactant side. Okay? That's what you did. You heated it up. And what's happened is that you've increased the capacity for that to hold more of the solution. So this is an endothermic process because of the fact that when you added the heat to it, what you did is you shifted it over to that side where it can hold more of the aqueous. And you don't need to have like a whole long litany of this. Just say, hey, it's endothermic, we heated it up, we stressed it, it held more, that shifted it more to the product side, it's an endothermic reaction. That's all you have to say. And most of the time, dissolution processes go like that, okay? They're almost always all endothermic. For example, this is why it's an abomination if you ask me. But if you like sweet tea, which I think is horrible.
Same.
Oh,
I'm with you there.
Wait, what?
sweet tea.
Oh, I'm not getting you more.
But that's a cult thing, though. I swear to God, that is the cult. It stops like a hell. But how they make sweet tea is they get it really, really hot, and they overload it with sugar so it's saturated, and then they cool it back down. And then it can't hold as much when it cools back down, and then that sugar settles out of the solution. So that's how that you know it's saturated. So if you ever bring me sweet tea, I will. Bad things are going to happen.
That's a pussy.
Anyway, so on E, so I would be surprised if you get done with the test and you don't have to write out some type of procedure, some type of lab question. They're kind of shifting towards that. So on E, equipment shown above, okay, the value of the molar heat of solution. So you're trying to find delta H. Okay, this is what you're trying to, y'all have done this before. What do you need to measure out?
Initial temperature.
Initial temperature,
Mass of the water.
mass of the water,
Mass of the
mass of the urea, final temperature.
What about the exchange in temperature?
or you can just do change in temperature. Okay?
Hey, don't make fun of them.
I would say temperature initial, temperature final, but that's just me. And those are the things that you need. So,
Wait,
when you get to F, so the entropy change is a positive value. So you want to calculate the absolute molar entropy of the aqueous urea. So how are you going to do that?
you add 7 like 104,
And what'd you get?
174.7.
174.7. Because of the fact that what they're saying is that if you look at this in terms of products minus reactants, okay? Start with that idea, products minus reactants. So, and if you look at this, it should make sense that, why should it make sense, and this is kind of this next question, why should it make sense that the delta S is a positive value?
Going from a solid to
Yeah, you're going from solid into an aqueous, okay? So you have more microstates, you have more degrees of freedom, there's more, however you want to put that. Okay. And then on H, it's got the student claims delta S the product due to thermodynamic stability of the dissolution. So basically on H, you want to look at delta G equals delta H minus T delta S. So here's the story. Your delta H, because it's an endothermic reaction, what's the sign of your delta H? Positive delta H. Now, we just established that you have a positive delta S. So when you have two positive signs, what does that mean? Temperature dependent. Temperature is above, temperature below. Temperature above. So what they're saying is that this is making it more thermodynamic favorable. Basically, you want to generate a negative delta G to make it spontaneous. And so that's what you need to say. You say, okay, hey, we're going to subtract that T delta S compound, or this portion of the equation, from a positive delta H. That'll generate a negative delta G. That's going to lead it to being spontaneous. Okay? Cool with all of that. Okay. That was a lot. Now, so that was that one. Speaking of London dispersion forces, try that 2019 question number 2. It has a list of like the I2 bromine across the top of it. Okay? So,
You want 1 and 2? Or just 2?
well, 2019 number 2 for now.
Okay.
Because that has a whole bunch of stuff in it that's going to be on the test on Thursday. So that's a good question.
But on that last one, can you not just say like Mother Nature likes increasing disorder? Just like delta S instead of delta.
Yeah. You say Mother Nature
Probably
likes
don't
something.
invoke Mother Nature.
Yeah.
It works in this class. I would understand
Yeah,
it.
wait, Birdcamp, what if I start talking about some chihuahuas and stuff? I might not get any credit.
If you say chihuahuas equal electrons, you're cool. But yeah, just don't say Mother Nature.
What if I say because Mother Nature's a lazy
No, okay. What if I say it increases the density of the universe? So that therefore it would make it
That would
thermodynamically
that would probably get you there.
Can I use the restroom?
Yes, go. All right, Mara, are we still going? Stop that.